So thank you all for joining us for this webinar. We are broadcasting our final class. Scott King and I thought to make this a formal class. We called it Geodynamics and ASPECT. Here in the room we have with us Dr. Scott King is here. We also have Dr. Claudia Adam, a research scientist who does mantle convection modeling. The students in this class are Shengshen Liu, Tahiri Rajaonarsen, and Grant Ewan. We also have in the room here with us Dr. James McClure, who works at the Virginia Tech Advanced Research Computing Center. So today we are going to just have some introductory comments. I wanted to describe to you how this class came to fruition. And then the students, Grant and Tahiri, will give a presentation about their first class project. The class actually consisted of two projects. The second project involved spherical calculation, and we would like to bring that into the open discussion at the end if there's time. So this is an image of one of the whiteboards from my lab, and I was explaining to my new student, Tahiri, all of the tools that he will need to learn in order to get up and running with ASPECT. So we recognize, and it's been recognized in the community, that ASPECT has a very steep learning curve. So in order to overcome this and get the students familiarized with the graphics programs that are needed, like ParaView or Visit, they need to learn how to use GitHub. Eclipse is a nice program when you're developing your own ASPECT plugins to become familiarized with Eclipse. There are a number of other tools that a new user of ASPECT we need to be familiar with in order to become efficient in using this code. So Scott and I both have a new student starting, and they are doing their research with ASPECT. So we formalized what we were thinking would be a one week, we would meet once a week and discuss our experiences with ASPECT. So we formalized this into a 1 credit course that was co-taught with Scott King's Geodynamics class. Now, the ASPECT community is one that gives back, and we do that by using GitHub. I have shown here the ASPECT GitHub repository. And when a person who's using ASPECT develops a tool or a plugin that's valuable to the broader community, we contribute that back by doing pull requests. So this entire it takes quite a bit of in-depth understanding of how ASPECT works, how all of the tools work so that you can develop a pull request. This takes quite a bit of effort and knowledge to be able to get to the point of submitting a pull request. So we decided that the first project would be something relatively simple, but would require the students to learn all of the steps that are necessary to eventually put in a pull request. And the ASPECT community should see that that was contributed last night by Grant. So just a little overview of how the class was structured. We would consider this a practicum course. The students received the geophysics or the geodynamics theory in Scott's geodynamics course. So this class was focused on implementing and learning each of the tools that were needed to run ASPECT. So there was it was dynamic. We would prepare the lectures. We would implement the lectures we had. We would run a few scenarios, come back together, discuss with Wolfgang and amongst ourselves what would be the best direction for the class. And you will see in a few moments that I think we were pretty successful. So I will now turn over this venue to Tahiri and Grant, who will give you their presentation on their first project.
All right. Well, Hello, everyone. As Dr. Stamp said, my name is Grant Ewan. This is Tahiri Rajal Narasan. Um, if sorry, Shanjin also did a fair amount of work on this project, but couldn't be here today. We'll do our best to go over everything the best of our ability. So, as has already been said, this class, the most basic purpose of this class was to get a feel for aspect, to try and learn its main use, see how it would pertain to our research. But um, as has already been said, if you're very new to this, like I am, for instance, brand new to computing, there was a lot more that had to be learned first, starting at the most basic learning of things like the Linux commands and using a terminal to go through directories, open and modify files to save those changes. That was really the first step to be learned. We had to learn more about the clusters on Arc that we would be using. I'll go over more of that in just a moment. Learning about logging in through the terminal using SSH was also something new. The output given by Aspect and learning how it was going to be visualized, we ended up downloading and using Visit for our output. All of these were new to us, and we had to learn them first. And then along with Aspect, we also got to learn about this community, some of whom we get to present to today, in modifying what already exists in Aspect. We learned some of the basics of LaTeX as well in order to modify the manual with the work that we've done. We learned a lot about GitHub. We have all our own GitHub accounts now. We have cloned our own versions of Aspect, made our own branches that we were modifying for this course. And specifically, our own interests for Aspect. I am a new student under Dr. King, and I'm looking at mantle dynamics of the planet Venus. And Tahiri is a new student under Dr. Stamps, looking at modeling mantle lithosphere interactions in Madagascar. So, the Aspect manual mentions this Van Keeken benchmark, which specifically looks at one part of one case from Van Keeken et al. Paper in 1997. That is case 1A, this isoviscous Rayleigh-Taylor instability. This actually comes in two different forms, both of which I'll talk about: the discontinuous case, or the discontinuous version, and the smooth version. So I'm going to start off with the one we started with, the discontinuous version. So the problem itself is a very simple 2D box. It has a compositionally lighter, less dense layer underlying a compositionally dense layer above, and the viscosity is the same for both layers and constant throughout. And the main thing that defines the discontinuous case is the interface between the two layers. It's given as the series of horizontal lines that kind of step down from left to right. You'll see there's also a gradual slope from the left to right, which causes an initial instability in the box. The interface is given by the equation for omega, which you can see is a cosine function. And if you look at a little excerpt of the file we have there from Van Keeken discontinuous PRM, the equation is given again in the file. Before actually running the case, we still had a little bit more to learn about the clusters we were going to be using. We specifically used one of two clusters. Shan-Chin and I were mainly using the Blue Ridge cluster, and Tahiri was mainly using the New River cluster. They're, for the most part, fairly similar. But before we could run the file, we had to learn how we were going to do this on the clusters. There is the most recent stable version of Aspect loaded as a module onto both clusters, Aspect 1.3, which we used for the first part of the class. In order for that to be used, we had to find out all the other modules, all the other parts that needed to be present before Aspect could be run. So we learned about the bash RC files, being able to know that whenever we logged in, all the modules that we needed would automatically be loaded and in place so that we wouldn't have to worry about logging in, seeing results from a previous job, doing some quick modifications and sending it off, and forgetting to have all of these things loaded so it would run correctly. We also had to learn the format for the submission script so that our jobs would be found correctly. They would know exactly what to do. They would know who to relate it back to and where we were in the university, nodes and processors to be used, and general wall time. So once we had all of that, we can get back into the first test we were running, which we ran in 5 different mesh refinements. That was the first thing we were really testing. We ran mesh refinements 5 through 9, and that corresponds to 5 refinements corresponds to a 32 by 32 mesh, 9 corresponds to 512 by 512, and this requires a little bit more editing of the PRM file. Main things we were looking at this stage were updating the output directory so that our results would go to somewhere expected and organized away from everything else. And very importantly, looking at the second box right in the middle, it says initial global refinement. Setting that will determine what refinement specifically is used. And what we quickly found with all of these small changes having to be made over and over was it was most beneficial to have several copies of say, the PRM file and our submission script with slight modifications made and saved between each one, so that all you would have to go do would be to go in and modify, say, the output directory. So we would have versions of Van Keeken discontinuous with refinement 7, like that example has in its title, already made, so we wouldn't have to worry about that detail. That made things go a lot more smoothly. So what you see now are some of our results that we got from the discontinuous case. Lined up by column, we have refinements 5, 6, 8, and 9. And then by row, we have time step 0 for all cases, their beginning step. About time step 400 for the second row. Third row is about 1200, and the final row is the final time step 2000. And what you'll see for all of them is, in general, they are the same shape, the same basic process has gone on. You see the refinement that you get from increasing the initial global refinement. However, if you look especially at the final steps for 8 and 9 in the bottom right corner, you see different structures between each one. You see an extra diapir forming in the last 2 panels of 8. It begins to form in the final panel of 9 as well. And this can be attributed to the difference in the first panel. In the first row, you see that refinement 5's division between the 2 layers is made up of 3 horizontal boundaries that step down to each other. Refinement 6 is made up of 4 horizontal boundaries that all step down to each other, and it changes by mesh refinement. So these discrepancies occur because the mesh is being changed, which is not desirable, and we'll go into how to fix that in just a moment. But before we're completely done with the discontinuous case, there was a little bit more analysis that needed to be done, specifically looking at the root mean square velocity. The formula for it given there, the little v within the integral is the velocity, and the larger one outside is the volume. So you'll see that the root mean square velocity was being taken over the entire box at one time step, which means that if you were to get a maximum of root mean squared velocity, you have a lot of motion in the whole box, which would most likely be associated with some major structural development, some large upwelling or some large sinking. And it was simple to learn to get how to get this information. It was, again, just going into the file. You can tell Aspect to give you statistics text file, and if you go into that, you'll see number 14 was column 14 will give you the RMS velocity, And you can plot that against the data in column number 2, which is the time. And if you do that, you will produce a figure such as this one, which we made and is in agreement with the figure that is in the ASPECT manual. You'll see that the first peak, which corresponds to the first major diapir going up the left side of the box, is very well converged for all cases, regardless of refinement. But after this first peak, there is a lot of discrepancy between secondary and, in a few cases, even tertiary features that come a lot more at random. And as I said before, this is more due to the mesh refinement than anything else. This is not the outcome we would expect. We would hope they'd be a lot more converged than this. So in order to fix this, we go to another version of case 1a, which is the smooth version. This version is very, very similar to the discontinuous. The major difference you will see is the boundary between the two layers is no longer a series of horizontal lines stepping down to each next one. It's now one continuous sloping line that transitions from one layer to the other. And this difference is given by the equation. You can see in our excerpt from the Van Keeken Smooth PRM file that the equation given to define the boundary is now different from before. The original equation is in there. There are new terms. A hyperbolic tangent is included over most of it, and an element that is called the smoothing parameter that Tahiri will talk more about in just a little while. We went through a very similar process for the smooth model. From what we had done before and keeping track of the run times for previous smooth model cases, we were actually able to get 10 global refinements out of the smooth model, so that gets us to a 1024 by 1024 mesh. And so here are the final time steps for all of the smooth model cases that we ran, 5 through 10. And you will see that, as before, they all resemble each other, but unlike the discontinuous case, there are no major differences between these pictures. There is the increased resolution that you would expect from increasing the global refinement, but other than the first couple of refinements, 5 through 7, where the picture changes quite a bit, when you get to 8, 9, 10, the final image is very, very similar, except for keeping the two layers more and more distinct as you go on. And so if you go through the same refinement, go through the same analysis as before of the root mean square velocity, you will see now that, just like before, the first peak is very well converged for all cases, and now the second peak is also much, much more converged than before. 5 mesh refinements is still a little bit of an outlier, but it's still much better to the discontinuous model, and any behavior after the second peak is fairly muted for this case. And so this is where the manual ends originally before our work, but it mentions at the end of it that in order to achieve even greater convergence, you can mess with a part of the equation from the smooth boundary that they call the smoothing parameter, and that you can scale this in reference to the mesh to allow for even greater convergence. So now Tahiri will take over for this next part.
So at the end of the Van Keeken benchmark cookbook section, it is suggested to use a smoothing parameter proportional to the mesh size in order to get more accuracy in the result and to compare it with the Van Keeken benchmark result in the paper. And this motivates our experiment to test the effect of the smoothing parameter on the calculations. And to do that, we are going to use the global refinement degree 7, because it gives us a balance between a fairly high resolution and a quick runtime compared to higher refinement degree. So in this experiment, we are going to modify the division part of the the interface function at the end, we can see in the arrow, which is 0.2. And we are going to use different value of this. So because for a global refinement 7, the size of the mesh in the vertical corresponds to 0.078. So we are going to use this value as a reference and test multiple values. And we are going to even test half of this value, which is 0.0039. So the evolution in time of the root mean square velocity is given in this picture, which shows that for all of the parameters tested, the first peak does not change significantly, while the second peak change according to the parameter, and the larger the thickness of the interface, the later the second peak start, and also the amplitude decrease proportionally. So this ends this part of this experiment. So for now, I am going to talk about another convection problem, which is also in the Van Keken paper. This is about the non-isoviscous Rayleigh-Taylor instability, which is different from what we presented before, which is use the same viscosity for the two layers. So to do that, we are going to set the top layer as 100 Pascal and test two cases in which the lower light layer is 10 Pascal and 1 Pascal, which gives us a ratio of 0.1 and 0.01. So one of the advantages of ASPECT is that we can modify the code as we want to set the simulation. And this is the case of the non-isoviscous Rayleigh-Taylor instability, because the spatial dependent viscosity is not implemented in the ASPECT code yet. So in this case, we modify the material model simple.cc and input our function for both discontinuous and smooth interface. And we have to compile again our version of ASPECT in order to do that. So when we modify the code, we have the way we test our code is that we print each value of the viscosity for each position, and plot this value and compare it with values that were calculated from other software like MATLAB. And we are going to test both discontinuous and smooth for the two contrast viscosity 0.1 and 0.01, so that in this case we have 4 cases. So our result shows that at the end of the temp step, we have these pictures showing that for viscosity ratio of 0.1, part of the higher viscosity fluid still remain at the bottom part of the box, while for 0.01 at the end of the temp step 2000, all of the light layer of the fluid are concentrated at the top of the boundary. So here we compare our result of the root mean square velocity from what is already presented in the Van Keken paper, and we can see that for higher contrast viscosity, the fluid rises faster, and its rise uh, uh, slower for small contrast viscosity, and this is actually consistent with the result obtained from the Van Keken paper, except that there are two peaks for the fluid motion, which is in the right part of the graph. And we actually recognize that by decreasing the global refinement degree, we could obtain similar pattern than this. And this will end my part of this experiment. And we actually have submitted this this work as our contribution to ASPECT. And
So yes, the final part of all this was the actual pull request, and so this goes back to what we were learning about the community, GitHub in general. We had to go through the process of getting accounts, getting LaTeX to be able to update the manual. We went in to the Van Keken part of the manual itself, added in our own work, put pictures from what we had done with the images already included, even put in a new table. And once it was compiled and built, we got everything added and ready to be committed, as can be seen from my screenshot from terminal. And once everything was ready, we pushed it back to repository on GitHub, and the official pull request was made last night. And this concludes our presentation on this subject. Thank you all for your attention.
Okay. So at this time, I think we can open up we can open up the floor for any discussion that there may be about this project, and then beyond that, there is some additional work that was done in the class on 3D spherical calculations that we would like to discuss as well, if there's no more discussion about this particular project. So are there any questions for Tahiri and Grant about the pull request that they submitted last night?
Yeah.
Julian is typing something.
Hey, can you guys hear me?
What's that? We heard something.
I was wondering if you can hear me, but I guess the volume is too low.
Yes, we can hear you now.
Is that better?
Yes.
Okay, I get an awful echo. I don't have a lot of questions or comments about the pull request because I haven't had the time to look at it, but it looks pretty awesome, and thanks for doing that.
Thank you. This was an experience.
I'm sure you get some comments and feedback very soon.
Yes. So Renee was asking you if you would add the PRM file, or yeah, add a parameter file that goes with it.
Oh, for the separate, the two different viscosity case must be. Yeah, I think we can go back through and find that. That's either going to be probably on yours or Shanjin's computer, but we can go back and find that. You have to, okay.
They are certainly expecting community feedback on their pull requests, so they're quite aware that this is not the completion of the project.
For the last part, the third part, did you? I was looking at the two plots and I was a bit confused if you managed to reproduce the results or if they were different.
Well, we were able to reproduce the result. However, we tested it with refinement degree 5 because in this result we use refinement degree 8, and the result seems having this second fix, but it does not match well. It is within some error.
Do you have an idea what could be the reason for that?
We are, at the moment, we haven't tried it at the refinement, the lower refinement that the paper originally tried it at. So we would like to try that first to see if that alone would be causing the difference. That.
Well, what we have in mind now is maybe we could test refinement degree 4 because in the method of Van Keken paper, there are different methods than the finite element method, and there to find the consistent global refinement degree, it's the same as in the paper. Is we need to run a couple of tests.
You got a couple of questions. Dr. Louise Kellogg asked you a question here. So,
well, most of them were challenging because for me, I was quite new using the cluster and aspect. The type of modeling we are using would not work on your own computer, and that we learning GitHub was also challenging, and we just started using Aspect, and going through all of the information was challenging. Yeah.
Mm-hmm. Yeah, I certainly agree with what you said. It was all kind of challenging for me. I think one of the more challenging parts of everything was just getting myself into the mindset of computing in general. Like I said at the very beginning, we're both pretty new to this. I have, at the beginning of the semester, I had almost no experience with any of this. When I said at the beginning that we were learning, Linux commands and how to go through terminal, I really meant that, like, I think Dr. Stamps told me at the beginning once to CD into something, and I had no idea what that meant, to just literally type CD and go into something. So I've learned, it was an interesting challenge to even just learn that. Is there something below that? Or...
Thank you very much for the hint. Yeah, that will be helpful.
Yeah. Mhm.
Would you expand a little bit on that, Renee? What do you mean by it would be, it's usually helpful if you're running many models again and again?
I can totally translate this. Like if you use, if you have a template,
Yeah. Just what is
you
it?
have a template file,
Yeah.
and you can basically script.
Everybody should have their mics enabled, so you
Yeah.
can
So
also
this is
talk as well.
okay. So this is James McClure speaking up. Go ahead, James.
So my understanding, based on what you've written, is that you want one sort of template PRM file, and then a shell script that will basically go in and create multiple versions of this file with different parameters using sort of just probably Z to replace specific lines. Is that correct?
Yes. Are there any more comments or questions about project one? If not, we could move on to discussing the 3D spherical calculation and some of the issues that the students ran into with this problem. Okay. So there are a couple of slides that we have prepared about their project, their second project. And would you like to? I do want to bring up just the main issues that came up. One of the main issues was that we were not able to run the spherical. We were not able to run aspect on more than one node. That was a pretty big challenge that the students ran into. Have any of you in the aspect community had a similar problem? And do you have any feedback about this issue? Including James McClure here, who is from ARC. Maybe he has insight too.
I have to see the details before.
Okay, do you know where it is in your presentation?
I have a case that I could run. Oh yeah, that's it.
I think we just mentioned the problem.
So I haven't seen that personally, but there are always problems with certain clusters and configurations and so on. So if you encounter something like this, you need to look at what are the error messages and then work with somebody, I don't know, an administrator or whatever, or somebody from us, from the community might also be able to help. And you go easier and easier, right? You simplify the problem trying to figure out what the issue is. So the first thing would be run a simple 2D problem on more than one node. If that doesn't work, you need to go to DO2 and run a DO2 tutorial program in parallel. If that doesn't work, you run an MPI Hello World program. And with that, you should be able to go to an administrator and say, look, this is broken.
One of the main problems we face is that actually the cluster, for example, New River, in which we run our model, uses MVP CSH instead of OpenMPI. And when we run the model using the MVP CSH, we can't run anything, even a simple model, using more than one node. But we have tested it using OpenMPI, and it is running. We can use multiple nodes. And when we were first sent to the ARC resources to report about this problem, is that maybe the way these resources are set up, maybe not like OpenMPI can distribute the calculation through the nodes, but NPP-CSH cannot with the actual version of ASPECT. Right?
I can take a look at this. If it works with OpenMPI, it's simple solution.
Well, that sounds like a configuration issue, either in the libraries or when configuring any of the dependencies due to or libraries or whatever.
Renee said, I had this problem on 2 clusters, but it was usually related to general problems on that cluster or the used MPI library. I agree with Timo.
What configuration MPI do most people use? Or is there a...
I think mostly OpenMPI.
Okay.
So do you have sort of nightly builds and tests? And if so, what do you use OpenMPI plus GCC for those?
Yes, those are OpenMPI and GCC, I believe.
Okay.
But in general, I mean, we've been running with Clang GCC, Intel compilers, Intel MPI, OpenMPI, and MPitch.
I've run DL2.
And I don't see a reason why it shouldn't work.
Mm-hmm. I think I'm fairly certain that DL2 benchmarks have worked, so there may be some glitch somewhere. I can look at it. You just have to do troubleshooting.
Sure, I mean, there can also always be bugs in our code.
It seems when Shengxing built it himself, compiling everything and using OpenMPI, he was getting more than one node. But when we were starting out, we were using a build that was all done with modules that had MPitch. And so either there was something in that build or there's some incompatibility on the cluster with MPitch and things. I didn't have Shengxing rebuild it with MPitch and see if his version also failed because we got it working.
There was also an issue with speed. So Shengxian reported that if he ran OpenMPI, if he ran ASPECT compiled with OpenMPI, it was actually slower than when it was compiled with MPitch. Has anyone else experienced that?
Well, that can also be cluster dependent, or it can depend on how this was configured and installed. Maybe you don't have the right interconnect or whatever.
Well, the other problem...
But yeah, to summarize, this stuff is hard, right? Getting stuff to perform well on clusters is really, really difficult. And there are a lot of details and a lot of things that can go wrong on every level, right? It can be hardware issues on a particular node. It can be software issues. It can be somewhere, whatever you installed could be wrong or off. And yes, in general, this is difficult, and there's no easy answer.
This is a new cluster too, so things have changed quite a bit over the course of the semester. So we'll just have to dig into it.
And yes, what Julianne is saying is really, really important. Never install MPI by yourself. Never, ever on a cluster.
So the other issue that we've had with spherical, and it's been hard because they've only been able to run on one node, but they're having a great deal of trouble getting models to converge with a convergence parameter of 10 to the minus 7. They're mostly having to back off to 10 to the minus 3 or 10 to the minus 4. And everything works well with Cartesian models, but as soon as we go to spherical, even a constant viscosity case without a very difficult thing, we're immediately having trouble with convergence. And I don't know if there's, how many people have been running spherical models and if there's any tricks there that we're not aware of.
We've certainly been running them, so I would be curious to know the exact setup to see what's going wrong and the exact error messages and so on. So that shouldn't be the case. I mean, linear solvers should converge.
So we were, once we can get running on multiple nodes, I had suggested that they create a small test that they could send to somebody else to verify that it's also failing on someone else's cluster and that it's not another issue of installation problems or something like that.
Yes, that would be great. Just send it to the mailing list and we will look at it.
I don't know if there's anything else if you wanted to sort of explain generally the 3D problem. What, some slides.
Julian says, I have run quite a number of 3D spherical models, but I usually use linear solver tolerance 1e to the negative 4. Yeah. Oh, that would be great if you would try it with e to the negative 7. Thank you. Do you want to explain any more about the 3D spherical calculation you did?
I think to really confirm that the problem does not converge, we want to retry it with multiple nodes, okay, because the iterations, which is taking time, and the cluster kill the job.
Because you have a version of it that got to like step 190 something after running for a while, but it didn't. Something about it was still was wrong. It was newly wrong.
Well, if there are no more questions or comments, we just want to thank you for joining this webinar. And are there any more comments in this room? No? Any more comments from the webinar chat room? Great. Okay, thank you so much.